Esteban, and she is going to talk on symmetry breaking in atomic multi-configuration calculations.
Thank you. Good morning, and well, I will not thank the organizers because I've been an organizer. Okay, so I'm going to speak about symmetry breaking. So many people here were in Munich in the spectral days in April, and I spoke about symmetry breaking, but it has nothing to see with that talk. It's not the same problem, not the same question, nothing. Okay, so this work I'm going to talk about is in collaboration with Mathieu Levin and Andrea Sabin, who is a chemist from Paris. Okay, so what is the multi-configuration method? So multi-configuration models are more or less intermediate models between Hartree-Fock and the full quantum mechanical models. In the sense that, for example, you want to compute ground states in a multi-configuration model, what you do is you have a Hamiltonian, you have your energy, and you want to minimize it in which class of wave functions. So the wave functions are actually linear combinations of certain configurations, and each configuration is itself a sum of Slater determinants whose coefficients are fixed such that the configuration belongs to a chosen symmetry subspace. So actually it's a linear combination of Slater determinants. Okay? So in the case of Hartree-Fock, we just take one Slater determinant. Here we take more, so the set in which we are minimizing is larger, and so the ground state energy will be smaller. And that's why people use this kind of models, because in some cases the approximation of the quantum mechanical full model by Hartree-Fock is too bad. It depends on the layers, how filled they are, etc., etc. So in cases in which the Hartree-Fock model is not very good, people use very often in computations multi-configuration methods. Okay, and so what is free? So as I said, the configuration have coefficients which are already fixed. Which is fixed is the coefficients in the linear combination of these configurations, and also the orbitals, the radial part of the wave functions in the Slater determinants. Okay, so this is more or less what is the multi-configuration method. Of course, if we are in the non-relativistic case, the method is called the MCHF, multi-configuration Hartree-Fock. In this case, the Hamiltonian is the usual Hamiltonian for a system of n electrons, which are near a nucleus of charge Z. And then in the relativistic case, what we do is to replace the Schrödinger operator by the Dirac operator. We all know here that this operator maybe is not well posed physically, but in all the in many computations in chemistry and physics, they use this Hamiltonian. They put it here, and they minimize the energy in this class of wave functions, and the results are quite good. So there is some kind of miracle. The Hamiltonian is physically not very well understood, but the results are quite good actually. So, so about these multi-configuration methods, we're speaking about these methods with some physicists in Paris some years ago, Eric Serre and myself, and we used to talk to them just to discuss models and to ask questions, etc. And one day it was not us asking questions, it was Paul Indelicato, who asked us. He told us, well, you know, we are seeing very strange things, because he saw our paper. We proved some years ago a result with Eric Serre in which we proved that you take solutions of the Dirac-Fock equation and you pass to the non-relativistic limit, you take C going to infinity, under some conditions you see that you recover the Hartree-Fock solutions of the ground states of the Hartree-Fock equation. Okay, so he saw that paper of us. And then he said, I don't understand, you seem to prove that things go well, that you can pass from Dirac-Fock to Hartree-Fock, and we have problems when we are dealing with multi-configuration Dirac-Fock, because the non-relativistic limit is not functioning well. It's not functioning well, I mean, there is a theorem, we can pass from one to the other. No, but it's not. So we spent some time thinking about it, but we left this problem aside. And then some time later, I was discussing with Mathieu and Andrea Sabin, and then we decided to look into this question. Okay, so what they say, for example, in this paper, but there are many papers in the literature speaking about this failure. They call it failure of the multi-configuration Dirac-Fock wave functions. So for them, it's really a failure. And so what they say is that for many years they've been using this MCDF method, And it was assumed by everybody that the wave functions obtained or computed by using this method reduced to the correct non-relativistic limit, without verification of the limiting values of L and S, which is a spin and angular momentum. And recently we found that the calculated MCDF wave functions sometimes fail to reduce to the eigenfunctions of L and S. So for them, the problem is that they compute the solutions for a given total angular momentum J is the sum of L and S, and they compute it, and they see that what they get for C sufficiently large is not an eigenfunction of L and S. And in the non-relativistic models, one prescribes in principle L and S separately, the spin and the angular momentum. Okay, so for them it was a problem. So just to fix notation, the angular momentum L, well, you all know what it is. The spin is just the components of the spin operator is just the Pauli matrix divided by 2. The total angular momentum is the sum of L and S. And if we have several particles, then the total angular momentum L is the sum of the individual angular momenta. Okay, so I said here, well, I didn't say it, but actually in this paper, what they analyze is in detail the case of beryllium-like atoms. So what they do is to consider atoms, well, nuclear potential, and then 4 electrons around it. Okay, so this is what they do, and they see that there is some problem, and so what they did is to take the same case and try to understand in detail what's happening. Of course, we understood, and we will see it later, we understood that the problem is related to the nonlinearity of the model. So we said that right away. The problem is because it's nonlinear, the model is nonlinear. But it was not enough, and in some sense we wanted ourselves to understand exactly what was happening, and also to explain to them exactly what was happening. Okay, so we decided to get our hands dirty and go into the details of this model. So no fancy abstract theorem or things like that. Really go into the configuration and try to understand what was happening. Okay, so we will consider an atom with 4 electrons, beryllium-like atom, and we will fix all the time that the total angular momentum is equal to 1. And so just for notation, we are working in non-relativistic models. The orbitals are called S, P, D, etc., depending on the values of the angular momentum little l. So S is for L equal to 0, P for L equal 1, etc., etc. But if we are working in relativistic models, we need to say more. It's not enough to say that. We need to give the values of J and L, the angular momenta L and J, because for a given L, there are 2 possible J's. Okay, so the usual notation for orbitals is like this. So the S, P, D, etc. stands for the value of L, and then you write here the value of J. Okay, so if you want to construct your atom by filling the first layer with 2 S electrons, and one with the spin up and one with the spin down to have orthogonality, and then you want to fill the next layer with 1 S electron and 1 P electron, what you have to do, the configurations they consider in this model is the following. So they take a linear combination of 2 configurations, in which in one configuration you fill the first layer with 2 S orbitals, and in the second layer you have 1 S and 1 P, here the same, but you distinguish. In the first configuration you have the orbital P1/2, and in the second configuration you take the orbital P3/2. Okay, so you have this, I will explain what these configurations are, but as I said before, these configurations are sums of combinations of Slater determinants such that they are eigenfunctions of the total angular momentum with eigenvalue 1. Okay, so this is for the SP configurations. But the SP configurations are nice, but if you make some computations, you see that the energies are not very good. You have interest in enlarging the setting which you are going to minimize, and so consider other possibilities. Okay, so you want to enlarge your set to diminish the ground state energy. So the next possibility is that you consider not only in the second layer 1s and 1p electrons, but you can also, the next possibility is that you can fill also the second layer with one p electron and one d electron. Okay? So in this case, you have 5 possible configurations. The first ones that we had already, and then 3 others, which correspond to putting in the second layer 1p and 1d. But then you have different choices, because the p can be 1/2 or 3/2, and the d can be 3/2 or 5/2. I hope that you remember your quantum mechanics to deal with all this notation. Okay, so so in the case of SP plus PD configurations, you have 5 possible configuration 5. Okay, so this is just for notation. So now, what means in this model that you are non-relativistic? Well, you are non-relativistic, then you don't distinguish the p1/2 and the p3/2, and you don't distinguish the d3/2 and the d5/2. So what means that the corresponding radial orbitals, these r's are the radial orbitals in the wave functions. So what it means is that you don't distinguish them. So the R2, which corresponds to p1/2, and the R3, which corresponds to p3/2, should be the same. And the radial part of the orbitals for the p3, for the d3/2 and d5/2 are the same also. So you insert this here, you just have a non-relativistic model. But if you keep the difference, you keep R2 and R3 different and R4 and R5 different, then it's relativistic, because you distinguish these states. Okay. So what most MCDF packages do is the following. You have your energy, you have your Hamiltonian. So if it's relativistic, you have this Dirac Hamiltonian. So you have your energy, and what you want to do is to minimize. You want the ground state, you want all the bound states, you have to look for critical points. You want the ground state, you want to minimize this energy. And what are your variational parameters? The variational parameters are the A and B, which were in the SP calculations, we had only 2 configurations, so we had only 2 coefficients in the linear combination, A and B, and then we have the radial part of the orbitals. Okay, so we have 6 unknowns that we have to vary in order to find the critical point or minimize. Okay, so this is this would be the MCDF calculation for the SP model, if you want, only. So you are just taking the second layer, one S electron and one P electron. Okay, so if you do that, you have to make some constraints, and the constraints that you want to normalize the wave functions. So you normalize the functions R, and then you have also to ask that the R0 and R1 are orthogonal, because you want to respect Pauli principle, and the R1 corresponds to the S electron which is in the second layer. So you need orthogonality there, and so you need that these R0 and R1 are orthogonal, and then you normalize also the coefficients A and B. So this would be a multi-configuration Dirac-Fock computation. You take this energy with this notation, you take these conditions on the R's and on the coefficients A and B, and you try to minimize analytically or numerically. Okay, so this you would want to do. Now some notation, because it's going to come next. Some notation also that is used in all physical books is that how you write the states which have, for example, just to give you an example, if I write, for example, 3p1 or something like that, this is notation. So this is a state which is an eigenfunction of S2, so the spin operator with eigenvalue S plus 1, of L2 with eigenvalue L plus 1, and the L is here, the S is there, and of J squared, which is the total angular momentum, with eigenvalue J plus 1. Okay? So for example, if I write this means that I am looking at a state which has L is an eigenvalue of L equal to 1, S equal to 1, and because I remind you that the L S equal to 1 means that the eigenvalue is S times S plus 1, and J equal to 1. Okay, so this is called a triplet P. Okay, so just this notation because it's going to come next. Second thing I wanted to say is that there is a theorem that is not very important, but where is a theorem which says that in this case also you take a ground state of this model of the multi-configuration Dirac-Fock, and you pass to the limit when C goes to infinity, you are going to recover a ground state of the multi-configuration Hartree Fock for the upper spinor, and the lower spinor will go to 0. Okay? So the non-relativistic limit works fine also in this context. So there is no failure of non-relativistic limit. The non-relativistic limit works fine. What happens is that the model you recover later is something that is not usual in non-relativistic quantum mechanics. And this is what I want to explain. Okay, so as I said, the problem is what you recover at the limit. You have to see what you recovered and try to see if you can identify for the solutions. The solutions are eigenfunctions of the angular momentum L and of the spin operator S. Okay, so what we have to analyze is actually the limit model that we obtain when we pass to the limit. So what we want to do is to look at the problem, which consists in minimizing this energy when H is the non-relativistic Schrödinger operator and body operator. And then we are going to take J equal to 1, which means that the eigenvalue is 2. So we are going to work in the class in which the psi's are eigenfunctions of J squared with eigenvalue 2. Okay? I remind you that J equal to 1 means that the eigenfunction, the eigenvalue is equal to 2. Okay, so we are going to analyze this model in detail. So this is the model. So for SP calculations, we have here the Hamiltonian. We have here the sum of 2, the linear combination of 2. Only 2 configurations are possible for J equal to 1. These are the ones. And now is when we get our hands dirty, because now we go into the details, and we need to go into the details to understand what is happening. So you can find in any good book of physics, you can find that these configurations, there are tables everywhere in the books, you know. And what you can see is that the first configuration, the one in which the P is in the 1/2, J is equal to 1/2. This configuration is a linear combination of the triplet P and the singlet P. It's called singlet. So this corresponds to configurations which are eigenvalues of L, J, and S, with L equal to 1. So we have P's. J equal to 1 I don't write because it's always, as I said. And then we have the singlet is S equal to 0, and for the triplet is S equal to 1. So these are the configurations, and this is the exact form of this first configuration. And the configuration in which we have 3 halves, here we have another combination. And these coefficients, as I said at the beginning, are fixed by the fact that we want that this configuration has J, is an eigenfunction of J, total angular momentum equal to 1. So everything is fixed here, okay? And I will tell you afterwards a little bit what this singlet and this triplet look like. Okay, so what is the problem we want to do now? What we want to do is to look in the SP case. What we want to do is to look at all possible configurations with J equal to 1, so linear combinations of these two guys, which means linear combinations of the triplet and the singlet P, and try to minimize this energy. And as I said before, the variational parameters are these 4 functions and these 2 numbers A and B. Okay, so this is what we want to do, and understand what was the failure. Okay, so now just to give you an idea, what is the singlet? And just to, I mean, it's useful. I mean, the proofs we need to know exactly the shape of these wave functions. So the singlet P is the sum of 2 slated determinants. You see here the slated determinant. You see the 2 S electrons in the first layer, one with a spin up and one with a spin down. And then in the second layer, you see 1 S and 1 P, minus the same guy but with the spins reversed. Okay, this is up down, this is down up, and you have a difference here. And for the triplet, you have the same thing, the same slated determinants, but you have with a plus. So yes, I keep it in here because afterwards we'll see that it's important. So the triplet is the sum of two slated determinants, and the singlet is the difference of 2 slated determinants. And I repeat that singlet means that S is equal to 0 and triplet S is equal to 1. Okay, so this is really when you have really to go into the details. It's a nasty problem because you have really to, if you want to do something abstractly, you don't see anything at all. You have to go into the details of the model. And just to give you an idea, if we go into the PD configurations, for the PD configuration, so when we are putting in the second layer a P electron and D electron, then we need the sum of 6 Slater determinants to realize a configuration which has the right properties. Okay. So all these numbers and all these things are in tables. There are tables in these books in which you find all this. Okay, so now what do we want to do? What we want to do is to look at this problem, which consists in minimizing the energy for j equal to 1. But for j equal to 1, we said that we have two possible configurations. We have basically in the SP calculation, we have the triplets and the singlets. So what we can do is to try to compare the problem which consists in minimizing over linear combinations with the problem which consists in minimizing the same energy but only over the triplets or over the singlets, okay? Because we know that any combination of these will be the test functions for this problem with j equal to 1. So what we know is that we enlarge, so these problems here are the minimization over triplets or singlets. Okay, now our problem consists in mixing them. So if we mix them, we are enlarging the set, so the minimal energy, the ground state energy, will be less than or equal the minimum of these two guys. Fine. Now, there is a rule in quantum mechanics which is called Hund's rule that in many cases physicists take as a theorem, but it is not. One has to prove it in every case. And the Hund's rule tells you the following thing. So it's something that takes place almost always, but I don't think it's always the case. Even if I don't have any counterexample in mind, but I don't think it's really a theorem, which says the following. You have two configurations which have the same values of L and J. The one which will have minimal energy will be the one which maximizes the value of S. Okay, so you have these guys have in common that they are eigenfunctions of J square and L square. And for them, they have the same eigenvalue. Then this one has the property that it's also eigenfunction of S square with eigenvalue larger. So Hund's rule tells you that when you have such two guys, the one which has minimal energy is the one with higher spin. Okay? So this, as I tell you, is called Hund's rule. And there are several Hund's rules actually, but this is the first one. And so what we do in this model is first we prove that Hund's rule is true in this context, in the context of the SP configurations. Okay? And the second thing we prove is that, well, these guys, one has less energy than the other one, so the minimum of the two energies is going to be the energy of the triplet. So what we prove next is that actually when we minimize over the mixing of triplets and singlets, what we get is the energy of the triplets. So there is no mixing in this case. When we want to minimize over all wave functions for j equal to 1, actually the model picks a triplet. Okay? So this is a case in which there is no mixing, and in the language of these physicists who wrote this paper I quoted before, there is no failure. There is no failure because when we minimize over j equal to 1, we find a guy who has a well-defined values of L, S, and J. Okay, so we prove this in this case, and so I'm going to try to tell you a little bit quickly how we prove that. So to prove Hund's rule is not a difficult result, but you have to again get your hands dirty. So what you want to do is the following: you take two wave functions which look almost the same. So we have a sum of Slater determinants. The first part is the same for the two of them. And in the second part, we see that we have the same guys, but only we have reversed the spin. Here is a spin up down, here is down up. Okay? So we have these configurations. And then we have a Hamiltonian, which is more or less like the one we have in our problem. But this theorem is a little bit more general. And then, if the interaction here is a function which is real and positive, and the positive is very important, and we will see later, then what you see is that when you form the energy of the sum of the two wave functions, you get a smaller energy than you make the difference. And remember that I left it here just for this. Remember that triplets is when we sum Slater determinants, and singlets is when we subtract them. So actually what we are saying, and we see already here, is that the least energy will be for the triplet. Okay? So how we prove this? Well, the proof is It's long but not complicated. I mean, long but tedious, but not difficult. So what you do is you compute the difference of these two guys, and since you have many configurations, you have to be careful not to make mistakes. And what you find is that in the end, this is equal to -4, the real part of this guy, and this guy is written here. So it's somebody that we see clearly that it has a negative sign if V, the potential, was positive. Okay? So we see that this guy is negative, since we have here a minus sign, this is positive, and this says that the triplet has less energy than the singlet. Okay? So this quantity is positive. So this proves, in this situation, the first Hund's rule. Second, how we prove that there is no mixing? How we prove that the minimizer, when we minimize over j equal to 1, we find the triplet. So what we do is the following: we take a wave function. So here, instead of taking the I have done is, instead of taking the sum of the configuration, I have used already the form, and the radial functions are here. I mean, it's another way of writing things. So it's the sum of a singlet and a triplet, and here I have the different. I mean, these radial wave functions. Okay, so this is a general shape for a configuration SP for j equal to 1. And then what we do is just to compute the energy of H psi psi. Okay, we compute it. We take into account the not overlapping of this, the orthogonality of you have different spin, etc., etc. I mean, you have again to do a tedious and long computation. But in the end, what you find, so you compute all these things, and what you see that the energy of such an element, such a wave function, is larger than or equal a positive constant, the difference of the energy of the singlet and the triplet plus the energy of the triplet. Since we already proved in the previous slide that the triplet has an energy which is less than that of the singlet, then this is positive, and finally we find that this energy is larger than or equal the minimal energy for the triplets. Since we have the other inequality by definition, we have equality. Okay? So we have seen that the minimal energy that we can achieve when we take SP configurations only for j equal to 1, we find the energy of the triplet, and this means that there is no mixing, that we find a minimizer which has a well-defined, it's a good eigenfunction of L squared, S squared, and J squared, and the physicists doing these computations are happy, no failure. They find somebody which has a well-defined value for L, S, and J. Okay, now let's go to the next. Why we go to the next? Well, we go to the next because if you consider, as I said before, only SP configurations, then the energy is too high. So they want to lower it, so they want to add more Slater determinants. So they are going to add, the next step, the PD configurations. So I said, this is what I said before, the notation. So in the case in which you have SP or PD in the second layer, you have three possible guys that appear in the configurations. The three possible guys are the ones that we already had before, plus appears a new one, which is called the triplet D, which is an element which has which S equal to 1, L equal to 2, and J equal to 1. So you have only these possible guys. So you are in the sector, let's say J equal to 1, and you are in the second layer with 4 electrons, with SP or PD electrons only. You have only these possible these guys who are at the same time eigenfunctions of L squared, J squared, and S squared. Only 3. Okay, so we have complicated the thing by adding a new one with respect to the previous case. Okay, so here, well, it's the same game. In the same game, we can define the energies of the triplets P, the singlets P, the triplet D. We can do all these partial things, and then what we want to do really is to minimize the total energy for J equal to 1 when we mix all these things. So the real, because when you are in the non-relativistic case, you don't have, sorry, in the relativistic case, you can't fix L and S. You have to fix only J. So this is the real problem if you come from a relativistic model. So you want to minimize for J equal to 1. So you want to minimize the energy for psi general. And so psi will be a combination of triplet P, singlet P, and triplet P. Okay, it will be a linear combination. And then, of course, since we are enlarging, we are taking linear combinations, the energy will be less than the minimum of the three partial minimization problems. Okay, so here the same question is going to arise. Do we have here equality or strict inequality? Okay, so this is the question which was posed in these physical papers. So the Hund's rule applies also in this case. It's the same proof I did before. So in this case, you can prove that the Hund's rule takes place, so you can compare the energies of the triplet P and the singlet P because they have the same L and J, and the only difference is the S, and so is the higher S which has a smaller energy. So this, the fact that the energy of this is less than this, even in the case of SP plus PV configuration, we proved already. Now, the second inequality here, we don't know how to prove it, and we don't think it's provable actually in general, but you can do numerics, or you can also use experiments, and it's clear that the triplet P has a much lower energy than the triplet D. Really, there is a big gap here, okay? But we can't prove that. This is not rigorous, okay? So by using this which is rigorous, and this which is based on numerical experimental observation, we see that among these three partial energies here, three ground states in the different classes, the one which is the candidate to be minimizer is the triplet P again. Okay, this is the smallest energy of the three of them. So the question is, do we have that the ground state energy for J equal to 1 when we have mixing is again, as previously, the energy of the triplet P or not? This is the question. And the answer we knew before we studied this, the answer was no, because this was the failure. This is why they were worried, because they didn't find this. Okay, so let's try to understand why this is not the case. Because this guy is the one which looks the best situated, because it has less energy than the singlets and the triple Ds. But still it's not going to be the minimizer when we take combinations. Okay, so just, well, here I just put some numbers, I mean, not important. We make computations to have numbers, and when you compute separately all these energies, you see that really the triplet P is the one which has lowest energy here. And we ran all computations we did in this paper were run by using a package which is one of the most popular packages in multi-configuration Hartree-Fock models, which is the ATSP package of Shea and Fisher. And actually for the cases in which you don't have mixing, you have SP or PD alone, you can run it online. You enter your parameters, you say compute, and you get the answer in, I don't know, in some seconds. It's really spectacular how well they have done it. If you want to mix the configuration, then you have to download the package and then do the computations yourself. Okay, so we computed all these things to have numerical values for all this. We computed the eigenfunctions, the R0, R1, R2, R3, for example, and you see that indeed, since we need orthogonality between the R0 and the R1 has one node. Okay, this is not important for the sequel. So the question is this. The question is whether we have a strict inequality here or not. Okay, so this is the reason why we have a strict inequality. The reason is we analyze in detail this problem. The reason is if you look at the first guy is the triplet D. If you look at the triplet D, you look at it in the set of all functions, okay? So you look at the energy. So you can prove that in the set of all functions, when you mix them, the triplet D is a stationary point of the energy, but it's not a local minimum. So if it's not a local minimum, it can't be a global minimum. For the singlet P, we prove the same thing. It's a stationary point of the energy, but it's not a local minimum. Same thing, but you see that there is a little difference because I use red and black. So what does it mean, the red and the black? Well, everything which is red is rigorous, and everything which is black is based on numerical computations. Okay. So the most important thing is when we arrive to the triplet P, this is our candidate to be ground state in the whole set. But what we prove, what we see, is that it has lower energy than the singlet, that is Hund's rule. Numerically, we see that it has lower energy than the triplet D. Okay, but which is incredible is that it's not a stationary point. It's not even a local minimum. It's not a stationary point of the energy in the whole set of functions. So if it's not a stationary point, it can't be a global minimum at all. Okay, so it's a dramatic thing which happens. It's not even a stationary point. of the total energy in the set of in the larger set. Okay, so so the corollary is that none of these guys can be a minimizer in the global ground state problem. So we have a strict inequality, and so this means that the minimizer that can be shown to exist can't be any of them. And if can't be any of them, since I told you already that these three are the only guys who have a given value, a definite value, a well-defined value, sorry, for L, S, and J, that means that the minimizer will not have a well-defined value for L and S. And this is the failure which was seen by this, in these papers. Okay. So what means is that in this case, there is mixing. So this mixing is in the I don't know physics, but at least in the chemistry literature, is called symmetry breaking. It's a different symmetry breaking that I am used to think about, but they call it symmetry breaking when you break the symmetry of the angular momentum. In some sense. Okay, and so this explains the difficulties they had to understand the non-relativistic limits. So the message is that the non-relativistic limit is okay, but what you find at the non-relativistic limit is not what you want to find in a non-relativistic model. Okay. So let me just I will not explain all of this, but just give you some ideas of how we prove these things. First, let's take the case of the singlet P. So I said that it is a stationary point, and also I said that it's a local minimum. Okay, and the students were in red, so I can prove both of them. So I'm going to tell you how we prove them. So we take a general wave function in the SP plus PD configuration. Well, I write it. I mean, don't try to understand everything, but well, it's like this, and the coefficients are fixed, except that they have by linear combination with A and B and C and D and E. Okay, so I have this linear guide, and so well, if this wave function is a singlet P, there is a list of requirements. This implies that we have these relations here. For example, A has to be A square root of B has to be minus B epsilon, etc., where epsilon is plus or minus 1. R4 has to be equal to R5, etc. So we have some requirements that are the requirements for this guy to be a singlet P. So to have to be eigenfunction of L square, S square, and J square with the right values. Okay. So we have this information here. And then we observe something which is very interesting here, is the following. Is that, well, you see, maybe you notice that I use different colors in the coefficients. It's not just by chance. So the different colors is, the green color is when I am in the singlet, and the violet is when I am in the what I'm saying, no, sorry, well, the green color is when I am with the R2, and the violet when I am in the R3. Okay. So actually, what we observe here in this, when we take into account these conditions, is the following: is that the ratio between the occupation numbers of the P1 half function R2 and the occupation number of the P3 halves R3 in the singlet SP and in the singlet PD are the same. Well, this is just writing this. Is when I look at the squares of these coefficients. This is the occupation number. Okay, when I look at this square here, and then I look at the other one, I see that the ratio is 1/4 in the SP singlet, and is 1/4 also in the PD singlet. So this is just an observation, but this observation is vital to prove that this guy is stationary for the energy. How it comes into play? Well, it comes in the following way. What I have is an energy, and I have some variational parameters, the radial functions and the number, I mean the coefficients of the linear combination of the configurations. And so what I want, if I want to see that the singlet P, the minimal one, is a stationary point, what I want to see is that the derivatives of this energy with respect to all the variational parameters is equal to 0. So when I look at in detail at the variational, at the fact that I have a singlet P, what I get is that the derivatives with respect to the coefficients is very easy to see that they are 0. And then what I get is this information. I get the information that the derivative of the energy at the point which is the minimal singlet with respect to R0 and R1 is equal to 0, good. But then I get this here, And this is linear combinations, and I want all of them to be 0. Because a stationary point has to be, all of these guys has to be equal to 0. But thanks to these magical formulas here, you can verify that there is a relation between this guy and this guy, which is given by this formula, and there is a relation between this guy and this guy, which is given by this formula, and it's due to the magics of the numbers, the occupation numbers before. Okay? And so, with all this, we can prove that all of these derivatives are equal to 0, and so the singlet P is a stationary point. The fact that it is not a local minimum is very easy to see. What you do is you have your singlet psi in red, and what you do is to modify it a little bit, you construct by hand something, so T is very small here, okay? So this square root is close to 1, and this psi prime is a well-chosen triplet that we construct by hand, and you can see that the energy of this thing, so you see that this thing for T equal 1, for T equals 0, sorry, we are at the value of the minimal singlet, and then when T is nearby, well, we are nearby the singlet, okay? And so you compute this energy, and you see that this energy is equal, maybe there is a lower order term, probably I forgot a lower order term, but it's equal to the energy of the singlet plus T squared, this difference here, but now we remember Hund's rule, which said that the triplet has less energy than the singlet. So this is negative. So what I have is that for T very close to 0, this guy is less than the energy of the singlet. So I construct by hand things that are below, so it's not a local minimum, because I see that this implies that the Hessian of the total energy at the minimal singlet has some negative direction. Okay, so it's not a local minimum, but it's a stationary point. Okay, so well, maybe I don't have maybe more time. So I had also a slide about proving that the triplet P actually, which was the candidate to global minimum, is actually not stationary. And the proof of this is based on numerical computations. Well, I don't have time. I prefer to finish with the last slide, which is the message that we have to keep in mind. So the message that we have to keep in mind is that in the multi-configuration model, if you choose a priori the values of L and S for an atom in its ground state, then you are not necessarily computing the ground state in the J equal to 1 sector. Okay? So you are not doing that because you can have, by mixing, you can get a lower energy. Okay, so this is the first message. The only reason for this phenomenon is the nonlinearity of the model, of course. We all know, for example, that when you prove Hartree-Fock, you look at the ground state of Hartree-Fock model, you have mixing the last layers. You have, depending on the atomic number. Okay, so we know that this is due to the nonlinearity, but when we said that to the physicists we were talking about, they wanted more details. That's why we looked into the details. So the only reason for this is the nonlinearity of the model. So the smallest state, well, this is what I already said, that the triplet P, which was the best candidate, is not really the ground state. You mix SP and TD configurations. And is there a recipe to avoid the failure, what they call the failure? Okay? Well, there is no recipe and no general theorem, because I proved to you that in the case of SP configurations, there was no mixing, but in the case of SP plus PD, there is mixing. So there are cases in which yes, there are cases in which there is no. Okay? So the only way to decrease the failure is to increase the number of configurations, to add other electrons in the second layer, like add F, G, H, etc. Of course, if you add and add configurations, what you are doing, we all know, is you are approaching the linear problem. So in the linear problem, there is no difficulty. Okay? So there is no recipe to avoid the failure. The failure is there. I mean, failure, you want to call it failure. For me, it's not. But if you want to call it failure, the only way to avoid, I mean, there is no way to avoid it if you add the configurations for lowering the energy. So either you don't lower the energy, so you take only SP configurations in this case, and there is no failure. But if you want to have a good estimate for the ground state energy, then you have to accept that when you fix J equal to 1, you will have mixing, and you will not have states which have a well-defined value for L and S. So this is the message. Thank you very much. So if I can take 1 minute, but it's not for the talk. So let me. I am going to complete the message of Mathieu. The other day, it was not he was shy and he didn't say enough, and I think it can be. So I repeat what Mathieu said. So we are organizing a 3-month program in the Institut Henri Poincaré in Paris. So it's the spring 2013, next year. We have a lot of activities. We have 2 one-week conferences and 4 one-day workshops. We have also summer school attached to it, near the sea, near Marseille in September. And we have lots, I don't know, but we have a good amount of funding. So there are people already who are invited, but if you are not and you want to come, you are welcome. We have funding to support people, especially young people. And in order to apply, you just go to the webpage of the Institut Henri Poincaré, or you go to the webpage that we prepared, and you can apply for funding. And you can come apply for funding just for come to 1 workshop or 2 workshops, or you can come outside workshops. You want to spend some time during this 3-month program. So we have money, and the deadline to apply for it is October 15th. So you are welcome to apply and go. Thank you very much.